Thank you, Terry. I appreciate that. And thank you, too, for supporting over these past 10 years the ICEP lecture series. It is a wonderful series which we hope will continue for many years to come. It's a great pleasure also to be here tonight to introduce this very special speaker. Nobel Prize-winning physicist Murray Gell-Mann is professor and co-chairman of the Science Board of the Santa Fe Institute and author of the popular science book, The Quark and the Jaguar, Adventures in the Simple and the Complex. Along with his impressive list of achievements, his term quark has made it to Webster's dictionary. Professor Gell-Mann has a long and distinguished list of academic experience and awards. A few of the highlights: his BS and PhD, both in physics, are from Yale and MIT respectively. His honors and awards are numerous and include honorary doctoral degrees from Yale, University of Chicago, University of Turin in Italy, Cambridge, and Oxford universities in England, to name a few. He is currently a member of the President's Committee of Advisors on Science and Technology, and he is Professor of Theoretical Physics Emeritus at the California Institute of Technology, where he taught from 1955 to 1993. Dr. Gell-Mann's Nobel Prize, awarded in 1969 in physics, honored his work on the theory of elementary particles. His eightfold theory brought order to the chaos created by the discovery of some 100 particles in the atom's nucleus. He found that all of those particles are composed of fundamental building blocks that he named quarks. Gell-Mann has many intellectual passions with lifelong interests in fields that seek to understand existence at its most complex: natural history, biological evolution, the history of language, and the study of creative thinking. His recent research at the Santa Fe Institute has focused on complex adaptive systems, which means systems that learn or evolve by using acquired information. The Institute brings together a wide array of great minds, from scientists to economists to linguists to historians. They are investigating things like similarities and differences among complex adaptive systems. These systems include a child learning his or her native language, a strain of bacteria becoming resistant to an antibiotic, or an artist implementing a creative idea. At the Santa Fe Institute, this multidisciplinary group of thinkers can talk freely, constrained, as Gell-Mann says, only by the need to agree with reality. The Quark and the Jaguar is Gell-Mann's own story of finding the connections between the basic laws of physics and the complexity and the diversity of the natural world. And now, to discuss the Quark and the Jaguar, Adventures in the Simple and the Complex, please give a warm Portland welcome to Nobel Prize-winning physicist Dr. Murray Gell-Mann.
Thank you. Thank you very much for that very kind introduction. It's wonderful to be back in Portland, in this very progressive city and state. I always enjoy visiting here. And it's particularly nice to be invited to give this afterword or epilogue to the presentations by Terry and Maynard. You've just heard how I've always been fascinated since I was a small child by natural history, linguistics, archaeology, and so on. All subjects characterized by individuality, diversity, and by evolutionary processes. And I describe in the book also how on entering the university, I nevertheless took up physics and then gravitated toward the theory of the elementary particles, the fundamental building blocks of all matter everywhere in the universe. Each kind of elementary particle, say the electron, is exactly identical to every other electron, everywhere in the known universe. All electrons are interchangeable. Furthermore, the laws of the elementary particles are essentially immutable. What is the relation then between these two very different, almost antithetic aspects of reality? The elementary particles and the complex systems that we see around us. In the title of the book and of this talk, the quark, elementary constituent of atomic nuclei, symbolizes the simple underlying laws of physics, while the jaguar symbolizes the complex world that we see around us and of which we are a part. And you heard how I assigned the name quark to these particular elementary constituents. It's an obvious name for the fundamental constituent of atomic nuclei. In the quark and the jaguar, I endeavored to trace the chain of relationships linking those simple laws of physics to the complex world of which we are a part. That would be a very daunting task, but it's made somewhat more manageable by adopting a particular point of view, the point of view of information. And when that's done, then we see that in the universe as a whole, and in substantial parts of the universe, complexity flows from simple rules, initial order, and the relentless operation over and over and over of chance. Now, the subject of simplicity and complexity I call plectics, from the Greek version of the Indo-European root plek, which is the main root of both words, simplicity and complexity. Simplicity coming from a Latin word which originally meant once folded, and complexity from a Latin word that originally meant braided together. That way, plectics is a description of the study of both simplicity and complexity. It doesn't commit you to discussing one or the other. You can use it as a name for talking about both. Now, what do we mean by complexity and its opposite, simplicity? It would take many different concepts, many different quantities, with different definitions, to capture all of the meanings of complexity and simplicity that are present when we use the words. And all of those concepts would be to some extent context dependent, not entirely intrinsic properties of the thing described, but dependent also to some extent on who or what is doing the describing. Now, the definition that comes closest to what we mean in everyday speech and in a great deal of scientific discourse as well, by the complexity of an entity, is what I call effective complexity. And for lay purposes, we can use as a definition of effective complexity the length of a concise description of the regularities of the entity. Now, it's important that we count just the regularities, not the features treated as random, incidental, stochastic. For example, take neckties. Fashions in men's ties in this country vary every few years. Men's fashions change only a little bit and rather slowly. It's not like the changes in ladies' fashions, but still, there are changes. Some years ago, it was the regimental stripe that was the most fashionable kind of necktie. Then we went through a period when more complex neckties were in fashion. This one is a little bit more complex. Now, once again, fashion has shifted back to the simple necktie. like this one. Now you see what we mean. We're talking now only about pattern, the pattern of the tie, as viewed from some distance away. And we're not talking about little irregularities in the weave. We're not talking about the soup stains, which you can't see from there. We're talking just about the pattern. And you see that the length of a concise description of the regularities of this tie is greater than the length of a concise description of the regularities of this tie. This tie is rather easy to describe as far as the regularities are concerned. This one would take longer. But you realize that a different observer might have a different set of values and consider different aspects of the tie to be the regularity. Suppose you're a dry cleaner. Then you don't care about the pattern. It's the stains that you consider to be the regularities. You're concerned about the soup stains, the little flecks of blood, maybe a tiny bit of ink, and the more different kinds of stains, the more complex. The pattern of the tie is irrelevant. If you're an inspector at a tie factory, then you might be concerned about little irregularities in the weave. You want to make sure that there aren't too many of them and that they aren't too big. And the pattern doesn't matter much and the soup stains don't matter at all. It's what you're concerned about is the irregularities in the weave and so on. So you see how what is a regularity and what isn't depends to some extent on the observing system. In any case, the effective complexity, the length of a concise description of the regularities, depends, of course, on what we call in physical science the coarse graining. That means the level of detail at which the entity is being described. If you look from afar at this tie, you're getting a very coarse-grained picture of it, and the regularities are even quick. You can describe the regularities that you see from there even more quickly. I'm a little closer, and so I can see a little more pattern here, and it would take me a little longer to describe the regularities that I see. So the effective complexity depends on the level of detail. It depends also to some extent on the language employed. It depends also on the knowledge and understanding of the world that's assumed when you begin the description. For example, if you want to describe a rhinoceros, it's a lot quicker if you already know what a mammal is. If you have to tell all about what a mammal is, then the description of the particular kind of mammal, that's the rhinoceros, comes at the end. But the most important feature of this definition is that it's a concise description. It's not redundant. In the book, I tell the story of a young woman teaching elementary school who assigns to her class an essay to be written over the weekend, a 300-word essay on any topic. And one pupil does what I used to do when I was a child, namely spends the weekend poking around outdoors and hastily scribbles something on Monday morning just before the class. And what the pupil writes is, yesterday the neighbors had a fire in their kitchen and I leaned out of the window and yelled, fire, 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 and so on. Now that's not the most concise description of what happened. He could have said, I leaned out of the window and yelled fire 287 times. So we're talking about a compressed description. Note how a scientific theory compresses into a very brief set of equations or a very brief set of words the regularities of a huge, even indefinitely large body of information. For example, Maxwell's famous equations for electromagnetism describe the electric and magnetic fields once you're given the boundary conditions and the electric charges and currents. And this works essentially anywhere in the universe. So a scientific theory is an example of a beautifully compressed description. Now that we're talking about fundamental theory in physics, we might ask, what is the status now of the description of the physical laws underlying the universe? I said before that they are simple. That's something that many of us believe. It's not absolutely proved yet. Maxwell's equations and other fundamental physical laws are now incorporated into a body of fundamental law, but we're looking forward to the time when it's all unified in a single unified quantum field theory that would describe all of the elementary particles, all the fundamental building blocks of matter, in other words, and their interactions, which would give all the forces of nature. This unified theory has been a dream of physicists for some years. What's remarkable is that in the last couple of decades, there is a wonderful candidate for such a unified quantum field theory. Just one candidate. It's called superstring theory, and it has many of the attributes that we want in a fundamental unified quantum field theory of all the fundamental particles and all the fundamental interactions. Maybe it's right. In order to know that, we have to do more calculations, extract more predictions from that theory, and also it would be desirable to do some more experiments. For that, we need a high-energy particle accelerator. Unfortunately, the one that was to have been built in Texas was knocked out by our House of Representatives. But now we can hope at best for the construction of the so-called Large Hadron Collider near Geneva, Switzerland. And the U.S. has concluded, I believe, an agreement to participate in the construction and use of that machine, and I hope it will go to completion. But that's not the only law. Even assuming that we can find the unified quantum field theory that describes all the particles and all their forces, there is another aspect to the fundamental laws of the universe, and that is the initial condition of the universe some 12, 15 billion years ago, whenever the expansion began. Now that initial state of the universe, around the beginning of its expansion, sounds at first as if it's very remote from ordinary human experience, as if you couldn't possibly care about something that happened that long ago. But in fact, it's very important for our everyday lives, because we have the so-called second law of thermodynamics that tells us that there is an arrow of time. Suppose you see a movie in which there are little bits of egg white and egg yolk and egg shell in many parts of the room to begin with, and in the film they assemble to form an egg. What would you conclude? You would conclude that you're seeing a film running backwards, because you know that as time goes forward, it's the opposite that happens. The egg splatters, and you get little bits of egg white, egg yolk, egg shell, and so on, scattered around you. It doesn't happen the other way. Now, why do we have this arrow of time? If you trace it back and back and back to its ultimate origin, the reason for that arrow of time is that some 10, 12, 15 billion years ago, when the universe began to expand, it was an especially simple condition. And if we look in time toward the moment when that was so, that's the past. If we look away from the moment when that was so, that's the future. So there's an arrow of time built in to the universe, and it comes from the initial condition. Now suppose you know the fundamental law. Say it's superstring theory. It may well be. And say you know the initial condition of the universe around the beginning of its expansion. Do you then know the history of the universe in principle? Of course, it would be difficult to calculate, but forget that. Do you know it in principle? Answer, no. In old-fashioned classical physics, the answer would have been yes. But we know today that the correct theory is quantum mechanical. And what that means is that what the theory can give you is probabilities for alternative histories of the universe. Just probabilities. There are many different alternative possible theories and many alternative possible histories, and what physical theory gives you is a probability for each one. So there is indeterminacy in the history of the universe, and furthermore, so that the history of the universe is co-determined by the fundamental laws and by an infinitely, well, say an indescribably long sequence of accidents. Accidents which are not, the outcomes of which are not predictable except for their probabilities. So you have the unified quantum field theory of all the particles. You have the initial condition of the universe near the beginning of its expansion, and then you have this fantastically long sequence of accidents, chance events, for each of which you have initially only probabilities. For example, if a radioactive nucleus decays, emitting, say, an alpha particle, there is no way to predict in advance in what direction that alpha particle will emerge. No way at all. All directions are equally probable. After it happens, of course, you can say. You look and see, you see the alpha particle came out in a particular direction. But before it happens, there's no way of knowing. Now, the indeterminacy provided by quantum mechanics is compounded by the fact that for any observer, most of the accidents that have already happened are inaccessible. We don't know how they came out. We know only how some of them came out, a very small number actually. Most of them are far away or hidden deep inside stars or planets or something of that kind. We have no idea how they came out. So besides the fundamental indeterminacy imposed by quantum mechanics, there's also the well-known indeterminacy that comes from ignorance. We simply don't know how a lot of those things came out, and that increases the indeterminacy. Then, besides that, even if the universe were classical and deterministic, there would still be the famous phenomenon of chaos. Chaos is in science, means the following. It means that in certain nonlinear systems, the outcome is extremely sensitive to tiny little details of what happens at the input. A lot of that occurs with weather. That's why it's so difficult to get exactly detailed predictions of weather in a particular place at a particular time, even with our very sophisticated apparatus of satellites and computers. They do a very good job of predicting weather, but they don't tell us exactly what the weather will be at a given time and place, which is what we usually want to know. Can we have the company picnic tomorrow or not? And part of the reason for that is that you have some degree of chaos in meteorology. So we have indeterminacy coming then from quantum mechanics, from ignorance of how a lot of the accidents of quantum mechanics came out, and finally from chaos. There was a beautiful demonstration of chaos that I saw in the Science Museum in Barcelona. They had a nonlinear version of the pendulum, and the visitor to the museum was supposed to grab hold of the pendulum, this nonlinear pendulum, and hold it in some position, and then let go or give it a push, either one. So it started out in a certain position and with a certain velocity, was then let go, and the visitor could see the motion of this nonlinear pendulum, but also the motion was recorded by a pen on a drum. Then the visitor was invited to grab hold of the bob again and try to do exactly the same thing. Try to give it put it in exactly the same position and give it exactly the same push or no push as before. Well, no matter how carefully the visitor matched the second event to the first one, you could see that the pendulum was following a totally different path. And that was confirmed by the pen indicating the path on the drum. That's an excellent demonstration of what is meant by chaos in science. At the end of the demonstration, I asked the director of the museum, who was also my Spanish editor, what are those two men doing standing there? And he said, oh, those are two Dutchmen waiting to take away the chaos. It's a strange remark. But it turned out that the exhibit was closing and was moving to Amsterdam. And they kept it open only for me. And the two Dutchmen were waiting somewhat patiently to dismantle the apparatus and carry it to Holland. But I wondered for a long time whether there wouldn't be a great deal of demand all across the world for two Dutchmen who could take away chaos. So because of this, all this indeterminacy, we can think of the alternative histories of the universe as forming a branching tree with probabilities at all the branchings. At every branching, there is just a set of probabilities. There are different possible outcomes. You can't tell which is going to happen until it happens. In a short story by the great Argentine writer Jorge Luis Borges, someone made a model of all those alternative histories of the universe in the form of a garden of forking paths, el jardín de los senderos que se bifurcan. And we can think of it just that way if we wish, a garden of forking paths or a tree of alternative histories for the universe. So think of all the accidents, all the chance events that have led to the existence of the people in this room. The accident, the little quantum fluctuation or whatever it was that led to the formation of our galaxy long time ago. The little chance events that led to the formation of the solar system, including the Earth. The particular accidental way that life began on the Earth. All the accidents of biological evolution that, together with natural selection, have shaped the forms of life that actually inhabit the Earth. The accidents that produced the special features of our human species. The accidents of procreation, of sperm meeting egg, that gave all the different genotypes represented here in this room. And then, given the genotype, all the accidents of life in the womb, of childhood, early adulthood, that led to the present situation. Remember that the genotype alone doesn't determine the person, also all the accidents that happen in the course of development. Identical twins, after all, have the same genotype, and they grow up into very different people because of their experiences. They have quite a lot in common on account of being identical twins, but still they're different individuals. By the way, that's something to remember in discussing cloning. A clone, a human clone, if ever produced, would be just a younger identical twin. Not anything mystical or peculiar, not a Xerox copy of a human being, just like an identical twin, but younger. Now, what about all those accidents? there are a gigantic number of accidents that occur all the time through molecular, atomic phenomena, subatomic phenomena, quantum fluctuations of various kinds. They don't all produce notable regularities in the world, regularities that we, for example, would care about. But now and then an accident occurs that has profound consequences, ramifications, lots and lots and lots of things happening in the world that are all traceable back to the particular outcome of that chance event. Those we call frozen accidents, accidents with a lot of consequences that are all traceable back to the same chance event. In my book, I mentioned, for example, the death of Prince Arthur of England, who was the elder brother of the man who became King Henry VIII. Arthur died early in the 16th century of some quantum fluctuation, no doubt. And Henry became the heir to the throne. Henry became king instead of Arthur. Arthur had been married to Catalina de Aragon, Catherine of Aragon, and Henry became the husband of Catherine of Aragon. Well, lots of things flowed from that. Henry later wanted a divorce, and that determined the particular way in which the Church of England left the Roman Catholic Church. Maybe that was inevitable, but it would surely have happened some other way if it hadn't been for that accident that got rid of Arthur. But the whole subsequent history of the English and then the British monarchy depended on that accident. And of course, all the references to Henry in all the history books, all the pictures of him on coins, all the things that he did in his reign and so on, most of those would have been somewhat different under the other king. And the whole history of the English and then the British monarchy down to our own day depended to a great extent on that accident. All the way down to the antics of Charles and Diana and the tragic death of Diana and so on and so forth. All of that could easily have been different if Arthur had lived. So that was certainly a frozen accident, I think a good example. There are numerous others from history and from lots of other fields. Now, where do the regularities come from in the universe? Remember, we said that effective complexity was the length of a concise description of regularities. Well, regularities come, of course, from the two fundamental laws of physics, the unified theory of all the particles and all the forces, and the initial condition of the universe. But we believe that both of those are quite simple, so they don't give much effective complexity. Most of the effective complexity, therefore, comes from the frozen accidents. The basic laws being simple, and the history of the universe being co-determined by those laws and all the accidents, and the frozen accidents being the ones that give rise to a lot of regularity, it's clear that most of the regularity comes from the frozen accidents, and therefore the effective complexity stems mainly from those frozen accidents. But you remember that the effective complexity was the length of a concise description of the regularities, and we agreed that which were regularities and which were features of an entity were treated as random or stochastic or unimportant depended to a great extent on the observer. So we have to have a theory of observers. What kind of a system can act as an observer? Well, Maynard, in introducing me, pointed out that it's a complex adaptive system, something that can learn or adapt or evolve the way living things evolve. Remember, with the neckties, we said that most people would classify the pattern as the regularity. A dry cleaner, though, would look at the stains, and so on. So that what is a regularity and what isn't depends on the complex adaptive system that's observing the entity in question. What is a complex adaptive system? Well, we can show a transparency that describes how a complex adaptive system works, provided I can learn how to turn on this machine. Well, it's remarkable. Works. Usually, as soon as I go near a piece of apparatus, it shatters. So, a complex adaptive system takes in a stream of data about the world, including some information about itself. It then picks out certain regularities in that stream of data that it receives, and it compresses those regularities into a schema. Remember, we talked about compression, what the school child didn't do in that essay. But the complex adaptive system compresses the description of the regularities into a schema. That's a word that I use borrowed from psychology. This schema is one of many possible schemata related by mutation or by substitution. In other words, you could have a different schema by altering the first one or simply by getting rid of it and changing it into a different one. Now, each schema, usually in combination with some more data from the data stream, is used to describe the world, certain features of the real world, or to make predictions about how certain things happen in the real world, or to prescribe behavior for the complex adaptive system as it exists in the real world. All of those, the description, prediction, or prescription of behavior, all of those then have real-world consequences. The description may be better or worse, the prediction may be more or less successful, the behavior may be successful or disastrous or somewhere in between. These real-world consequences then exert selection pressures back on the competition among the possible schemata. So it's a kind of feedback loop from the real world. The more successful schemata generally tend to stay, the less successful ones tend to be eliminated. I should say, by the way, that my colleague John Holland has also written about these things, and he uses a slightly different set of terms. What I call a complex adaptive system, he calls an adaptive agent, and what I call a schema, he calls an internal model. And he reserves the term complex adaptive system for what I would call a loose aggregation of complex adaptive systems. I'm sorry to confuse you with this other set of terminology, but you might run into it in reading. Both John and I, we're very good friends, both of us are illustrating the old saying that a scientist would rather use someone else's toothbrush than another scientist's terminology. Now, we can give some examples of complex adaptive systems. In biological evolution, the genetic makeup of an organism, the DNA, the genes, constitute a schema. The schema is subject to mutation from generation to generation, and the schema, the genotype, unfolds in the presence of the environment, in the presence of development, as we said before, to give the developed organism. And the survival of that organism and its production of offspring that survive and so on help to determine the survival of schemata with similar patterns of DNA, with similar genes. And if the developed organism doesn't survive or doesn't have offspring, then that doesn't favor the continuation of similar genetic patterns. We mentioned the scientific enterprise. That's also a very good example of complex adaptive system. Here, theories are the schemata. And as I write here, they're robust when they've had successes, but they're still subject to modification. And the Whether they agree with observation affects their viability in a positive way. And of course, if they disagree with observation, eventually you have to get rid of them. So the scientific enterprise is a wonderful example of a complex adaptive system. Now, I should mention parenthetically in connection with science that these days there are a lot of enemies of science, various kinds of social constructionists and deconstructionists and so on and so forth. You find them lurking in philosophy departments and places like that, sociology departments. And these people emphasize that there are other selection pressures in science, and they're quite right. There are other selection pressures. Occasionally, there's selection pressures that, so to speak, shouldn't be there, stemming from occasional fraud, from power relationships, somebody more powerful imposing a theory on people who are less powerful, and things of that kind. Greed, excessive ambition, and so forth may be factors. So it isn't just the repeated comparison with nature that's used that determines whether a theory is accepted or rejected. It's also all these other factors, including prejudice. That's all true. And when we count the selection pressures that exist in the scientific enterprise, we have to include these other things also, because they're really there, although they're not so frequent as is alleged. For example, fraud is actually extremely rare. It seems to exist mainly in biomedical research, where the occasional doctor paints mice, something of that kind. But there is some fraud, and there is some imposition of authority and all of these things. What's nice about the scientific enterprise, though, and what the enemies of science don't seem to understand, is that the repeated comparison with observation of nature purifies the whole enterprise. Eventually, all these other forces are overcome by the force of selection pressure coming from comparison with nature. So eventually we realize that cold fusion is baloney, that polywater doesn't exist, that the prejudices against Einstein's theories of relativity were merely prejudices, and so on and so forth. Human societies can also be considered complex adaptive systems. Here, the schemata would be institutions, customs, traditions, myths, and so forth. They play the role of schemata. They're a kind of cultural DNA. Richard Dawkins has even suggested that analogous to the gene, we have the meme, which is a kind of unit of cultural DNA. And these memes, in the presence of the environment of the society, lead to societal behavior, the success of which affects the viability of these schemata, the institutions, customs, traditions, myths, patterns of behavior, and so on. A business firm is a complex adaptive system with strategies, policies, corporate culture, and so on as the elements of the schema. Selection pressures correspond to profits, share prices. They give feedback that affects the competition among schemata. When things don't work very well, the schema is mutated. Or even a radically different schema is adopted, usually under a new CEO. Nowadays, we have complex adaptive systems on computers. Computer software has been developed in a number of cases that allows the computer to evolve, for example, strategies for dealing with a situation with a clear payoff. Say, strategies for playing a game that no human being has ever thought of. For example, what I write here is the individual instructions in a program for the computer may undergo random mutations. And there's a tendency introduced for those changes that improve the play in the game to be retained, those that make it worse to be eliminated. And it's in that way that the computer can evolve strategies that may never have occurred to a human being, but are effective. So every complex adaptive system on Earth is connected in some way with life. but maybe very indirectly. These computer software packages, for example, are connected with life only in the sense that some nerd alleged to be alive has created them. Now, of course, complex adaptive systems make errors, identifying regularities that aren't there, or ignoring regularities that are there. In our human experience, we may characterize identifying regularities that aren't there as a kind of superstition. Frequently, we find regularities in the world around us that aren't really there, and superstition is a very good set of examples of that. When we see irregularities and just deny them, that's what we call denial. That happens a lot too with us human beings. And probably all complex adaptive systems have cases where they identify false regularities, the way we do when we have superstitions, and fail to recognize true regularities, as happens to us when we're in denial. Complex adaptive systems show a tendency to spawn other complex adaptive systems. You can have parts of a complex adaptive system that are complex adaptive systems, for example, our brains or our immune systems. You can also have aggregates of complex adaptive systems that act like complex adaptive systems. You can go from a single-cell organism to a multi-cell organism. Societies can aggregate to form bigger societies, as our colonies did when they formed our country in the late 18th century with the motto, E pluribus unum, out of many, one. Now, you heard a little bit about our institute, the Santa Fe Institute. It arises in part from the need to study similarities and differences among all these systems, mammalian immune systems, human learning and thinking, biological evolution, the prebiotic chemical evolution that led to the first life on Earth some 4 billion years ago, learning by computers. So we need people, in order to study the similarities and differences among these very different systems, we need people who can range across many fields, but we need people also, they may be different people or the same people, who are responsibly familiar with the subject matter of each of the subjects concerned. If we're going to have a team of people looking at some question, and it will include observations on language, we need a great linguist around to make sure that one isn't doing crank linguistics, fake linguistics. We need a respected economist to make sure that the economics is not crank economics, and so on and so forth with all the different fields. So, as you heard, we have at the Santa Fe Institute, at various times, we have mathematicians, computer scientists, physicists and chemists, evolutionary biologists, neurobiologists, immunologists, ecologists, population biologists, anthropologists and archaeologists, political scientists, economists, historians, and psychologists. It's a visiting institution. There are only 2 or 3 scholars who are there long term. Everyone else is a visitor for a period from a day to 5 years, depending on who it is and what kind of visit. But there's a very widespread family of Santa Fe Institute people who have been there or are coming there in the future or correspond by fax or email or phone calls or exchanging graduate students or something with the other people. And so we have a far-flung Santa Fe Institute family of hundreds of scholars and scientists around the world. At any given time, there are maybe 40 to 50 resident at the Institute. Now, why is it so difficult to do this kind of work at our great research universities and institutes of technology? There, the barriers between disciplines are very rigid. It's very difficult to get a lot of interdisciplinary work done. Sometimes there is an interdisciplinary institute at one of our great research universities or institutes of technology, but it doesn't get a lot of respect somehow. This interdisciplinary institute may be headed by some famous scholar or scientist who earned a reputation in a conventional field and can now afford to do this kind of thing. But the institute is typically housed in a dilapidated Victorian house near campus, or a shed built for temporary use during the First World War. And the junior members of the institute are usually not tenured, don't have a great deal of influence on teaching or research policy or on hiring. And in general, it's not taken so seriously as it might be. And the reason for that is not just stupidity. There is a very good reason why the barriers are fairly high, and that's because our present system for measuring excellence depends so much on these fields. We have departments, dissertations, professional societies, journals, sections of granting agencies, and so on, and they're all disciplinary. They all depend on a particular field. And so excellence is measured in a field. And we know how charlatans love to cower in the crevices between fields. We're familiar with the kind of person whom the mathematicians think is probably a good physicist, the physicists think is probably a great mathematician, and so on and so forth. So the universities have a good reason for maintaining their barriers, and they're very slow to change. They change ponderously. The system of lectures, class lectures, covering the ground of some well-established subject was set up in the days before the invention of printing. And yet we still have the system. The universities have apparently not noticed the invention of printing. The seminars at the Santa Fe Institute may be on foraging strategies of ant colonies. They might be on how to make money by observing fluctuations in financial markets and predicting the amplitudes of future fluctuations. There may be seminars on the development of banks in Florence in the 14th century. There could be seminars on how metabolic rate scales with mass in mammals or plants, and so on and so forth. A tremendous variety of subjects. You've all heard of the work of Dr. David Ho and his team at Harvard on the AIDS virus. And what isn't generally known is that most of the theoretical work was carried out at the Santa Fe Institute, largely by people from Los Alamos. Well, SFI, the Santa Fe Institute, is itself a complex adaptive system, self-organizing and changing. We hope that the Institute will facilitate research and advanced teaching in the field of simplicity and complexity and complex adaptive systems, what I call plectics, and that it will help the great research universities and institutes of technology by challenging them to break down eventually the disciplinary barriers and take a crude look at a whole system instead of always breaking it up into parts, and by providing a forum where many of their great researchers and advanced students are encouraged to make connections. That's the main thing, to make connections. And someday we may even influence our schools where the opportunity to make connections is wasted all the time. Thank you. Let me close by saying that complex adaptive systems may well exist in many different parts of the universe. I don't think they're close enough so that they've already visited us. I think that's largely superstition. But in very remote parts of the universe, there may well be other complex adaptive systems. There doesn't seem to be anything terribly special about our planetary system. Must be lots and lots of planets in the vast universe. And there doesn't seem to be anything so terribly difficult on a planet like ours in having life start. It started very soon after the heavy bombardments by celestial objects abated. So probably there is something like life in many different parts of the universe. Whether our intelligence and self-awareness, which seem to be higher than those of the other animals on Earth, whether our level of intelligence and self-awareness is impressive on a cosmic scale, we don't know. We don't really know. As Pogo in Walt Kelly's comic strip said to another swamp creature in the Okefenokee Swamp, just think, out there on planets circling other stars, there may be beings more intelligent than we are. Or maybe we are the most intelligent things in the universe. Either way, it's a mighty sobering thought. Thank you. Thank you very, very much. Do you want to can you take the questions and I'll answer them?
Okay, start over here. Go ahead. All right, Sarah, someone there at the mic? No, they're walking away. Where's the first question? There you go. Go ahead. Yeah, go ahead. Sorry.
Yeah, I have a statement and a question. First, I'd like to say that you're right on with the idea of interconnectedness and in learning and educational systems. It's definitely the way to go. I know from experience. And second, I was wondering how exactly you consider simplicity and complexity. Do you consider them opposites?
Yes.
And how so? How is simplicity not just a lesser form of complexity?
That's why it's the opposite. You have more complexity or less complexity. The less complexity you have, the more simplicity you have. They're just opposites.
All right. I'd also like to I'd also like to ask, how does a system choose which schema to first use before it to kind of kick off the cycle?
Oh, that's a very interesting question. The question is, what determines what schema a complex adaptive system begins with? And that's to a great extent a chance process. I mean, it's presumably a schema with some degree of appropriateness, but otherwise there's a big element of chance in where you start. Think of a human being getting an idea. Your initial idea is determined by a whole lot of accidents of your experience, probably. It's undoubtedly not a totally inappropriate idea, or you wouldn't have it. But it may well be wrong, it may well be succeeded later by a much better idea. But the original one occurs to you because of all sorts of historical circumstances in your past. So I think that's generally true, that some past influences, in part accidental, determine where a complex adaptive system begins with a schema. But what's wonderful about the process is that under these selection pressures, the schema is likely to become more suitable later, wherever it starts.
Thank you.
Yes, Bob? Go ahead.
Thank you for coming, Dr. Gell-Mann. I was always impressed with Carl Sagan's version of the Urey-Miller experiment, and I was curious where the Santa Fe Institute was taking the prebiotic chemical evolution. Could you comment on that?
Yes, I was at Chicago, and Harold Urey was a colleague, an older colleague in 1952, 3, 4. Stanley Miller was his student, and I remember when Stanley Miller did the experiment with Urey as his supervisor, in which he had simulated lightning in an atmosphere of ammonia and so on and so forth, and then little creatures crawled out. No, they didn't really. But I remember that experiment very well, and Miller has spent the rest of his life working on ideas about the origin of life on Earth. And at Santa Fe Institute, many of our members of our Santa Fe Institute family have worked hard on this problem of the origin of life. It's still not by any means solved. There are lots and lots of different ideas, but the various ideas are getting developed more and more, and presumably eventually we'll really learn something about it. It's a favorite subject. We don't do much observational work. There's no law against it. We haven't got a resolution declaring that we will never do observational work, but our institute is primarily theoretical and computational, using pencil, paper, and computer. And we just authorized, actually, the first observational project, which is a project on ant behavior in Costa Rica, social insect behavior. But as time goes on, I assume we'll have some other observational projects, but we do mostly theory. And theory is very important in this question of the origin of life on Earth.
Thank you.
Yeah, over here.
The strong consequence appears to me to be a more valuable result of the accommodation process of the schema. The strong consequence appears to me to be stronger, more valuable than a weak consequence in the process of the mutation.
You mean strong selection pressures?
Yes.
Yes, of course.
In your book, you have defined war and tyranny as evil. Yet they are the sources of very strong consequences in regard to the evolution of the society. Is it reasonable to define these things as evil?
Well, most people find them, let's say, uncomfortable.
What is your foundation for calling war evil?
I don't think did I use the word evil, actually?
Yes, sir, it's in the book.
Maybe I did, I forget. Anyway, most of us consider war and tyranny to be somewhat undesirable when we're experiencing them. It could well be, though, that hundreds of years later, if we live hundreds of years later, we might celebrate the consequences of such a period. For example, as I mentioned in the book, one of the themes in human history is the progression, although with a great deal of hesitation and a great deal of recoiling from time to time, the progressive enlargement of the units that we consider to be us, from households to tribes to city-states to countries to great big regions and so forth. And in many cases it was conquest by a tyrant, in fact. So both war and tyranny that led to the enlargement of these polities, which later on, of course, was a good thing that they were larger because you had peace over a bigger area. I think many of us would prefer, if possible, to attain this kind of enlargement by more peaceful processes, like the union of our colonies or the union of the Swiss cantons to form the Confederation of Switzerland and so on. But war and conquest certainly were one of the mechanisms that produced it historically. So you can certainly argue that in many cases these things that are so uncomfortable to experience lead to consequences which later on produce a great deal of happiness. That can happen.
Could you speak a little bit about the feedback that you got over the 5 years of during the establishment of the Santa Fe Institute in terms of strong and weak consequences which mutated?
You mean for the Santa Fe Institute itself?
Yes, sir.
Oh, yes, there were many. Many of our ideas were validated and have now applied to what we do. Other things that we thought of doing turned out to be a very poor idea. For example, we thought of having regular students granting degrees. Well, it soon became obvious that if we wanted to grant our own degrees, we would have to get accreditation. To get accreditation, we would have to offer conventional courses, and pretty soon we'd be back in the conventional environment from which we had escaped. So we decided not to do that. We originally thought of having a great many permanent people. We were never able to raise the money for that. We have now gone pretty much to the opposite extreme of having virtually no permanent people, but just visitors for periods ranging from a day to 5 years. And that seems to be working fairly well, actually, this turnover process. So there were many ideas that turned out to be fine, like looking at simplicity and complexity in complex adaptive systems, like working in interdisciplinary teams, like establishing far-flung research networks around the planet. All of those worked out fine, but some other of our initial ideas turned out not to be good ones, and we abandoned them. So we are an evolving organization.
Over here.
Susan? Yes. You mentioned that complex adaptive systems can find irregularities that don't exist.
Regularities
that don't exist,
yes.
like superstitions and things like that.
Right.
And that they can also deny regularities.
Correct. Correct.
Is there anything adaptive about denying a regularity?
Yes. In the case of our human behavior, you can look at denial. For example, denial of death. It's one of the most prominent regularities. And we see that it gives comfort to people. And it allows them to function, whereas they function better, perhaps, than if they were constantly aware of it and constantly frightened of it, and so on and so forth. I would attribute a lot of superstition and a lot of denial in human beings to fear. But this fear may itself be adaptive, to some extent at least. So, yeah, you can see some advantages, certainly.
How about the advantages of things like superstition?
Well, the same thing. Superstition can make you feel good. You imagine there's something taking care of you, everything's going to be all right, and that may help you to function very much better, even if that something isn't there.
Thank you.
Up above.
Hello. You mentioned that the Santa Fe Institute was theoretical predominantly rather than experimental.
Yes.
And I was wondering if there's a lot of people there working in artificial life, and I was wondering if you could comment on that and whether you thought that was an experimental science.
Well, computational work, I wouldn't particularly pick out artificial life. Computational work, such as many people do at the Santa Fe Institute, is a sort of virtual experimentation. You set up a model of some kind on a computer and you fiddle with it, or you learn how the computer software itself functions and so on and so forth and study that. And that is like a virtual experiment. You're running an experiment on a computer, so to speak. But I wouldn't call that experimentation on the rest of the world. It's different. But you can think of it as a kind of virtual experiment. Now, artificial life is just a particular way of slicing, modeling the world. You can distinguish modeling life from constructing computer models of all kinds of other things. And I don't think that's a very good way to slice things, but it has certainly caught on a lot. Chris Langton, I believe, gave it the name and has sort of led that effort, and it's extremely popular. We've published several books on it at the Santa Fe Institute, and they sell like hotcakes. And Chris Langton's conferences on so-called artificial life have attracted a huge number of people, but I myself wouldn't slice it that way. To me, the subject is the study of complex adaptive systems. Some of them represent life, some of them represent social systems, some of them represent complex adaptive systems on computers, which are not alive, and so forth. And I would just look at them all as constituting one subject. But Chris divided them up so that some of them are called artificial life.
Thank you.
Is there somebody over here? No.
I'm a nerd and I freely admit it.
Now, wait a minute. I have here my credential. It says Massachusetts Institute of Technology, Nerd Pride. I don't wear it in my shirt, however. I ought to wear it in my shirt.
The gentleman behind me said I've been certainly out-nerded. I'd like to ask you about a couple of things. You had mentioned starting out with a starting point, establishing some simple rules, and observing some probabilities associated with the outcome. Then we moved to accidents, and we've also talked about chaos.
Yes.
Could you comment, please, on which might be a subset of the other? It was a little confusing for me.
Oh, what I said was that quantum mechanics requires that the fundamental dynamical law plus the initial condition do not determine the history of the universe. All they give is a set of probabilities for coarse-grained alternative histories of the universe. So that's one fundamental source of indeterminacy. Now, that makes the histories of the universe already a branching tree. So there are a lot of accidents, one after another, that are occurring and that co-determine the history of the universe along with the fundamental laws. But then I said, we don't know a lot of those, the outcomes of a lot of those accidents. No observer can possibly be aware of the outcomes of all the various accidents, because most of them are hidden. So that's another source of indeterminacy. Then I said, even in the limit of a determinate science, like the way classical physics used to be, even in that limit, for nonlinear systems, you still have effective indeterminacy, because in many nonlinear systems, you have chaos, so that the outcome is indefinitely sensitive to tiny details of the input, and therefore the slightest smudging of the input leads to indeterminacy of the output. And that's yet another source of indeterminacy. You have to compound all of these to get the total indeterminacy. And as a result, the histories of the universe really form a branching tree with lots and lots of different ways that you can have accidents.
Thanks a lot.
Here.
A two-part question. First, is it possible to view understanding as a complex adaptive system, understanding being
Yes,
human thought?
very much so.
And given that, what can that teach us about our ability to, or our innate limitations in understanding the natural world?
Well, I don't know about innate limitations. A lot of people talk about them and try to think about them, but I don't know that we've established innate limitations except these fundamental unpredictabilities that I described. Apart from that, I don't know that there are permanent, rigid limits on our ability to understand the world. I think it's remarkable how well we can understand the world. It looks as if the world is put together in such a way that you can understand it very beautifully. Could so easily be different. Murphy's Law doesn't seem to apply. It's like mushrooms, you know, edible mushrooms. Murphy's Law doesn't apply there either. The most delicious mushrooms and the most poisonous mushrooms are both rather easy to detect, if you know what you're doing. Could so easily be the other way.
Above? Yeah.
Thanks for your talk today. I work in the field of information and was very interested in what you've been covering tonight. My question for you is if you've pondered this particular thought and if you've got people at the Institute working on it. You've given a lot of talk tonight about complexity and information and how the more complex something is, the longer the amount of information is needed to describe the system.
To describe its regularity.
Yeah, to describe the regularity, yes.
Right.
And also about the theory of everything, how...
it's not a theory of everything.
Okay.
A theory of the particles and their interactions.
That's good, because that's what I'm trying to touch on.
I explained that it wasn't theory of everything, because you have to combine it with all those accidents and with the initial condition of the universe.
Okay. My question is this. Is information itself another state of matter? Because when I think about it, it seems to me that in order to represent information, you need matter or energy in order to do it. And so is there a theory of everything that includes not only gravitation and matter, but also information?
I wouldn't put it that way. I would say that although I'm very interested, obviously, in the informational point of view, I've described it, that's what I've been describing this whole evening, that I don't regard it in that way. I regard the informational patterns and the informational approach as mathematical and abstract. But this mathematics of, say, a complex adaptive system, which is defined by its mathematical structure, if you like, can be instantiated in the real world, can be represented in the real world. The laws of physics permit examples of complex adaptive systems to be present in the real world. And that's not the same as their definition, which is an abstract one and lies more within the realm of mathematics. So that's how I would define the position of information. That the informational point of view, informational description, is a mathematical pattern, which, however, can be found in the real world because the laws of physics permit it in various cases. We mentioned a number of examples of complex adaptive systems in the real world, all of which are permitted by the laws of physics.
Thanks.
You're welcome.
Over here.
Many avalanches are small, and there are a few large avalanches, and as Per Bach talks about, the systems tend to evolve to a critical state where their sizes obey a power law. In the branching tree of possible universes, some quantum events seem to have big consequences, like the one that led to King Arthur's death, a big avalanche. Can we study whether quantum events and their repercussions obey the same sort of a law, a power law distribution?
Well, Per Bach emphasizes correctly, in my book I actually mentioned that. He emphasizes that when you have things like earthquakes that obey a power law distribution, scaling law, it's called the Gutenberg-Richter Scaling Law. It's just a power law distribution for the energies of earthquakes. Richter, of course, invented the scale, the logarithmic scale for earthquakes. The logarithm of the energy released is proportional to his index. When you have something like that, the very, very big events lie on the same curve as the very small events, which are so numerous. But the small events are generally not very important in their consequences. If you have a 1.5 earthquake, it's not even reported in the newspapers. It's a blip in some seismology graduate student's notebook, but it's not reported anywhere. It doesn't have any profound consequences usually, unless it happens to knock over a fragile piece of china in somebody's house that's worth $1 million. And then maybe it would get reported in the papers and it would be a frozen accident, but it's pretty unusual. Whereas if you have an 8.5 earthquake near a city, that's a big deal. That makes all the history books, it causes deaths, it causes huge property loss. It's for us human beings at least, it's a very important event with lots and lots of ramified consequences. It's definitely a frozen accident. And yet it lies on the same curve as the small event. Per emphasizes that a lot, and nothing wrong with emphasizing it. But in some cases, we're not sure that that's really how it works. With extinctions in the paleontological record, Per Bach laughs at the event that created the Chicxulub crater 65 million years ago. Says, oh, you can always find an explanation of some kind, but it's just a curve, and it's just one item at the top of the curve, and so on. But we don't know that that's really so. He and his friends assume that the fundamental mechanism for paleontological extinction is interspecies competition. It's an internal mechanism, And if an external thing like that small asteroid or large meteorite that created that crater 65 million years ago, if an external event like that happens, he thinks it just precipitates an event which, on account of internal interactions among the biological organisms, would have happened anyway. Well, we're not sure that's true. It may easily not be true. Am I answering your question?
Well, my question was whether we can study the ramifications of a quantum event, the size of the ramifications, not whether it really will obey the power law, so much as whether we can.
Well, we have to try to trace certain things to individual events. For example, there is a theory that each galaxy was actually, that the condensation of each galaxy was actually precipitated by a single fluctuation, but we don't know yet if that's true. It's a hypothesis. But as time goes on, I expect we'll learn more and more about it as we do better and better calculations and compare them with observation and so on. So yes, in some cases I think we will be able to trace the effects of individual events. We already can, of course, when we make measurements of quantum events in the laboratory. The only way we make a measurement of a quantum event is by having it amplified to a classical level in a piece of apparatus so that we actually see it. And there, of course, we're observing the magnification of a quantum event every time we make a measurement.
Your breadth of approach kind of reminds me of James Burke's work, and something that we don't usually see in traditional education. I was wondering if, other than books, is there any kind of a motion or groundswell at the Institute to put together a documentary series or something like Carl Sagan's work or James Burke's work based on the Institute's work with the complex adaptive systems?
Well, people do come and film us and present the films in various places. That happens. So far there hasn't been anything major. I wouldn't mind actually participating in such a project. And right now I'm in conversations with somebody about it, but it's still fairly, it's still just a glimmer in somebody's eye. A gleam in somebody's eye. It's not really a project yet. Now, so far there hasn't been a major film presented to a huge audience about this kind of thing, the way Carl's work and Burke's work and so on have been presented to huge audiences.
Well, I look forward to such a thing.
Oh, it would be fun. Thank you.
Over here.
Okay, you mentioned chance and random actions a lot, but couldn't you argue that nothing is truly random?
No.
That, well, I'm not arguing for fate or anything, but couldn't you argue, like, say somebody's life hinges on, like, the roll of a dice or something, somehow, and so they roll the dice, and somehow they lose all their money and, I don't know, end up in jail or something. Couldn't you, if you went back in time, tried that over again, why would his throw be any different?
Imagine it's a quantum event. I mean, something that's obviously a quantum event, like the disintegration of a nucleus. Mm-hmm. You could hook something up. This is like Schrodinger's cat. The first part of Schrodinger's cat story. The second part is utterly stupid, but the first part is correct. The first part of the story is correct. Namely, you could hook up a situation where if a radioactive decay goes into the right hemisphere, it sets off a hydrogen bomb and blows up a city. Mm-hmm. That's better than just killing a cat for this purpose. And if the radioactive decay goes the other way, it doesn't set off a hydrogen bomb, it doesn't blow up the city, okay? Mm-hmm. Now you have a huge consequence flowing from a quantum accident which is absolutely unpredictable. There's a 50% probability of the alpha particle going to the right and a 50% probability of it's going to the left, and whether the city gets blown up depends entirely on that.
But
that's chance.
Yeah, but if you could do that once and say the city survives, if you could go back in time somehow and try that again, why would something else happen? I mean,
I said it's chance. It's random.
Okay.
Unpredictable.
Thank you.
Hard to swallow. Up above?
Hi. Before I ask my question, I just want to make sure that everyone's got your last name right. I know that my last name has been pronounced wrong for my whole life, and now I don't correct anybody anymore. So what is your last name for sure here?
And what is your last name?
Mine is Swartz, and I get called Schwartz, and I don't say anything about it anymore because it's been happening for so long. So is it like Gell-Mann or Gell-Mann or Gell-Mann?
Either one. Either one.
50-50 chance?
Okay, so here's my question. Dr. Gell-Mann. I'm a layperson, so I think of things sort of in a conceptual way. So I hope that you're with me on this. I think of what has been called and what I like to think of as emergent properties a lot.
Yes,
and I think of emergent properties like looking at the lights going across a marquee and how you can see them as individual lights blinking on and off, or you can see it almost like a motion of lights.
Right.
And I think of the chord coming out of the three notes in a triad. And I think of consciousness as being an emergent property. Mm-hmm. And I know that Francis Crick talks about this with his idea that all the neurons flash at a certain frequency at the same time, and that's somehow what's responsible for consciousness.
No, that's not. That's supposed to be solving the binding problem, maybe. That's a conjecture about how to solve the binding problem. It doesn't directly address the mystery of consciousness.
Well, I certainly know when to address the mystery of consciousness.
It's an interesting mystery. I mean, the question is, how do the biological properties give rise to consciousness? I don't regard it as a mystical question or one that requires some mystical new force or something of that kind. It's just an unanswered question as to exactly how it arises and what the threshold of complexity is that's required to get consciousness. Could we, for example, someday in the distant future have a computer that has consciousness? Probably, but it may be too difficult to do. But in principle, it's probably okay. We just don't know.
Well, what I'm wondering is there a way to measure the constituents that comprise the system that results in an emergent property? And is there any way of measuring whatever kind of connections or interactions those components must have in order to produce an emergent property?
Yes, but it may be difficult in certain cases. I regard emergence in the following way. I describe it in my book, although I don't use the word very often. I should have used it probably more often. Let's take physics and chemistry for a very simple example. Chemistry is based on physics, but you don't get chemical phenomena except if there are certain conditions present. The temperature and pressure have to be within a certain range. If the temperature is too high, the atoms and molecules come apart and you don't have chemistry. You may have nuclear physics, but you don't have chemistry. That's the case in the center of the sun, for example. It's too hot for chemistry. So chemistry comes from physics plus certain conditions that have to be true for you to have chemical phenomena. So chemistry is derivable in a sense, in principle, from physics plus these special circumstances. However, it's not the best way to look at chemistry. Some chemists have won the Swedish prize for theoretical work in which they derive chemical concepts from physics, but mostly chemists use these concepts on the chemical level. They talk about chemical bonds, they talk about reaction rates, and various other chemical ideas. Even though they're based on physics, physics plus the special circumstances that allow chemistry to exist. Well, those chemical properties you can regard as emergent properties. You don't need something new in order to get them. You don't need special chemical forces, such as people used to postulate hundreds of years ago. They come out of the regular forces of physics. But they look like chemical forces. They emerge from the physics plus the accidents and give you what looks like special chemical laws. Well, today most of us regard biology the same way. Life does not require special new vital forces. As far as we know, it's based on the ordinary laws of physics and chemistry, plus a huge amount of additional information that specifies the accidents that gave rise to the particular kinds of life we have on Earth. And then in other parts of the universe, I'm sure there are things like it as well, with their own special accidents. But given the physics and chemistry and given these accidents, you can, in principle, describe life. But that's not the best way to describe life. The best strategy for looking at life is to combine this reductionist effort with a look at life on its own terms, as a biologist looks at life. That's a much more successful strategy. You can try to connect it with chemistry and physics plus accidents, but you can also look at it on a biological level. It's an emergent phenomenon. In the same way, I am sure that consciousness is an emergent phenomenon, just as you say it is. It emerges from biology plus special accidents of primate brain development, and gives rise, in a way that we don't understand at the moment, to the phenomenon of consciousness. Perhaps it could also exist in computers if they're complex enough, but we have no idea how that would happen. So emergence means that you don't need something new in order to get something new.
Go over here.
Doctors Kaufman, Chalmers, and Penrose have all shared with us their struggles with their perception that it's difficult to get emergence from one well-organized phenomenon to another. My sense is that you don't share that sense that it's so difficult. Is that true?
I don't have the vaguest idea what they're talking about.
That's pretty definitive, thank you.
Go ahead.
Hello, Doctor.
Well, one of them I've never heard of, but the other two, I don't know what they're talking about.
Hello, Doctor.
Yes.
I'd like to ask your opinion on something that I see as something of a conundrum. If Western culture in the 20th century is an adaptive system, I'm wondering if, as technology moves towards something that we're calling the information age, I see artists moving towards what might be called a rise in nonsense art. And just to give some documentation, I'm thinking of Jackson Pollock, among other modern artists, Philip Glass's minimalist music and the 20th century classical music, James Joyce's Finnegan's Wake, from which I believe you derive the word quark, and Ella Fitzgerald's ability to scat. So as a culture, are we in fact hedging our bets on the technology information question?
I'm sorry, I missed something in what you said. What did you say about nonsense?
Yeah, I think there's a rise. 20th century artists tend to produce what I might call nonsense art with...
Well, there is some, but I didn't think what you mentioned fitted into that category.
Simply that it doesn't convey... It conveys less of particular statements rather than just random... It seems to be the true element in jazz or Jackson Pollock's is sort of glorifying the random elements, whereas technology is moving towards eliminating the random elements.
I don't seem to agree with those statements.
Okay. Well, thank you.
But it's a very interesting set of ideas. I just don't follow them very well. I'm sorry.
Some up above.
Technology, in information technology, has made it possible to share very rapidly and across the world a lot of bits, which are called information, and technically they're information. But most of it is garbage. Most of it isn't true, it's badly organized, it's useless, and so on. And one of the great tasks of our civilization is to try to extract some degree of knowledge, understanding, and maybe a smidgen of wisdom from all these bits. And art contributes its share, including the artists you mentioned. The Santa Fe Institute tries to contribute by synthesizing material from many different disciplines. But the reward system is broken. That is, the rewards for extracting useful understanding from this welter of partially false, ill-organized stuff, the reward system isn't very good. The free market, of course, is always subject to a certain number of distortions, and here it favors entertainment and it favors sales, but in the long run it will favor the generation of understanding that's desired by some particular industry, for example, or some particular business. But wisdom and understanding that are needed by the community at large will not necessarily be generated by the reward system that we have or are getting. So we need to do something to fix it. It could be that, for example, private foundations and other not-for-profit organizations of civil society could help by subsidizing excellence in synthesizing, filtering, and so on, these bits to extract wisdom and understanding from them. But that would cover art as well as science and literature and so on. It would cover a lot of different things.
Let's go with the question. The people that are just standing now, and that'll be it. So, Dave?
Dr. Gell-Mann, first of all, thank you for coming and talking with us this evening. My question has to do with, I noted your time interval at California Institute of Technology somewhat matched up with Dr. Pauling's. And in your expression of the work at the San Francisco, or the Santa Fe Institute, does that kind of point out that there may be, and I'll try to ask the question quickly so I can finish, did that point out that perhaps at the California Institute of Technology it may be, for lack of a better word, a cradle of cross-discipline interest?
Well, Caltech is organized in such a way that you would think there would be a huge amount of cross-disciplinary work. What there has been is the sort of cross-disciplinary work between two disciplines, say, two or three, that represented by biochemistry, geochemistry, and so on and so on. So, for example, nuclear physicists and astronomers work together. Particle physicists and astronomers have not worked together very effectively, despite the fact that the two fields are practically merging. Caltech has a division of mathematics, astronomy, and physics. This is an age in which not only nuclear physics, but also elementary particle physics is coming very close to astrophysics and cosmology, but not at Caltech. Mathematics and physics are reuniting after years of estrangement caused by the mathematicians using incomprehensible language. The mathematicians are now moving much more toward what they used to be, trying to explain what they're doing. And mathematics and physics are becoming reunited, but not at Caltech. So I wouldn't say that Caltech has a particularly strong tradition of this kind of thing. It's set up in such a way that it should work, but it works only in some cases and not in others.
So one up above there? Go ahead.
I have to say that I haven't read your book, and so...
Well, you should remedy that as soon as possible.
However, you may have answered this, and I may be redundant, but where would you estimate that in the formation of the universe, the first accident occurred where...
Well, that's a little hard to say, but you know, it could be that there were several different possibilities for the universe right at the beginning, and there was a kind of choice that took place, which was the first accident. That's not ruled out.
So, was the first little glob of matter that turned into the universe, was that inherently not ordered at all?
We don't know. Going back that early, this is in the first 10 to the minus 44th seconds of the universe. You're asking about that?
Yeah.
We just don't know that much about it yet. People are working on it, but it'll take some time, I think, to understand better what happened.
Okay.
So I can't give a definitive answer.
It's a good question, though.
Thank you.
Well, the question's fine. We just don't know enough.
You over here?
Yes, thank you. I didn't find the argument of the nonlinear pendulum wholly convincing.
Argument?
Yeah.
I didn't give an argument. I gave a description.
The example, excuse me.
Yeah, the example, okay.
As wholly convincing for the existence of chaos. I believe it was Albert Einstein that said God doesn't throw dice.
Well, first of all, Albert Einstein was wrong. That's the first thing.
Could you give me another example?
The second thing is,
could you give me an example?
The second thing is the chaos. The phenomenon of chaos exists even in the classical limit in which Einstein believed. It represents an extreme sensitivity in nonlinear classical systems, the kind Einstein liked. In nonlinear classical systems, the outcome can be extremely sensitive to the tiniest details of the input.
Sensitive doesn't mean unpredictable, though, does it?
Well, it means predictable in principle if you get the initial condition absolutely right.
So theoretically, there's no chaos.
No, there is chaos. Chaos means that there is an extreme sensitivity to tiny changes in the initial input, and in practice, for example, in this museum example, the visitor found it impossible to get the second setting so close to the first one that it would give a similar path for the pendulum. If the visitor had gotten it exactly the same, of course, it would lead to the same motion.
Well, that's impossible since he couldn't do it at the same point in time.
No. It's repeatable later on in principle. The thing is, you just don't get it accurate enough. And what the exhibit shows is that no matter how hard you try, you always have a little change from the first episode, and that gives rise to a very different motion. Whereas if the system were not chaotic, the tiny little change produced by that change in the tiny little change in the initial condition would give us a very similar path. For example, a linear pendulum would give a very similar path, even if you did make a small mistake. The nonlinear pendulum of this particular kind has the property that the tiniest mistake makes the path very different. And that's what the museum exhibit demonstrates.
But given no mistakes, we get the same result.
Yes, classical, yes.
Thank you.
You right there, over here. Those two.
All right. It seems that nothing is perfectly simple, perfectly simplistic, and that nothing is perfectly immune to reacting to actions upon it. So I was hoping you could explain your definition of a complex adaptive system a little bit.
I did.
I was a little bit. It's okay. I was a little bit confused. That's all.
You don't want to repeat that.
I could be like Paul Dirac. Paul Dirac was asked a question once that was, somebody said, I didn't understand your derivation of such and such. Silence. The chairman of the meeting said, Professor Dirac, are you going to answer this question? He said, I didn't hear a question. The person said he didn't understand. So the chairman said, well, could you could you explain it again? So Dirac repeated exactly what he said before. So that's perhaps what I should do, but I'm too tired, so I think I will.
Just a couple more.
That's enough. I can't do it.
That's enough? Okay.
Sorry.
That's it. Thanks.